Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay. Right. So we are very happy to have Ariel Pickers here from Harvard University. And Ariel's work spans two fields. He did foundational work in both of them. One is industrial organization, the other one is econometrics. And in I/O, his specialty is structural I/O, which means that, for example, you take an industry like the car industry, you estimate a cost and demand system, so the production and demand side, and then you can do, because you have the model, the underlying model of the industry, you can do, for example, counterfactual. What happens when you change a policy? What happens when two firms merge, etc. Now, this is already hard when you do that in a static game, where all the decisions are taken at the same time. But when you do this in a dynamic context, it becomes even more complicated because decisions are taken over time. Past decisions influence future decisions. And so a lot of his work in recent years has been in dynamic games, and this has dynamic gains and asymmetric information, so it's super complicated. Right?
I'm hoping it will be simple by the time we finish, but you never know. This is John. We're with Chaim Frischman, who's at Tel Aviv, and so two things. One, I'm probably used to talking to a different audience, and you're probably used to hearing from a different kind of person. So if there's something you don't, if I'm saying something in phraseology you don't understand, somebody should speak up. And if any questions, you should speak up. It's a long talk, but it doesn't matter if we don't get through it all, because it sort of goes in parts. We miss parts, it's fine. It's much better to have a conversation if somebody has it. So let me just go over what I put in a couple of slides of background because I knew it was a different kind of audience. Okay. So there's parts of this literature that I'm involved in, the industrial organization literature, that's really been developing tools to analyze responses of markets to either an environmental change, price of oil, or a policy change, a tariff, or a merger policy. Okay, so that's the goal. That's the overall goal of this thing. Okay, and it's taken its analytic frameworks from game theory. So, each agent does actions which affect the returns of all agents. Okay, and the equilibrium or rest point condition is typically some form of Nash equilibrium. So the policies that would be played at a rest point would be policies such that no agent has an incentive to deviate. Just that would be the condition. Okay. So I want to move to so we've done quite a bit on static games actually, and we've, I don't know, successful or not, but like government agencies and firms and things are using them. Okay, so you can argue that it's not successful, that they're using it wrongly, but that's different. Okay. But we've had a lot more trouble with dynamic games. Dynamic games are games where the state variables, that is, the variables that determine each agent's profits. Okay, so there's a bunch of variables to determine each agent's profits. They evolve over time in response to the controls chosen by the agent. So like an investment game, or they can be an asymmetric information game, which I'm going to come to in a second. Okay. And typically what goes on in these models is the state variables evolve as this Markov process. So you make enough assumptions so that conditional on the states today and the actions today, that's all you need to know to the distribution of states tomorrow. So it becomes a controlled Markov process. Okay? And the equilibrium of some form of Markov perfection. That is, no agent has an incentive to deviate at any state on the space. Okay? At any one of these tuples of... So these kind of simple notions of equilibria have been very useful in what I call toy models, which are used by my theory colleagues. Okay, so they're used to, and they've been very useful. I don't mean to say this derogatorily, but they explore, they've allowed them to explore possible outcomes in a structured way and illustrate how various phenomena can happen, leapfrogging, collusion, all sorts of stuff. Okay, but when you take them to real-world market situations where you try to put in the complexity that you need to mimic a real-world situation, they just become unwieldy, okay? And two things occur as a result. It limits our ability to do dynamic analysis, just from an analytic point of view, from a researcher point of view. But also it leads to the question whether there's some other notion of equilibria which better approximates agents' behavior. I mean, if we can't do it with some of the best, given a year and some of the best computers, it's not clear that that there isn't a better way. It's all going to be an approximation. Okay, we never can do it exactly right. The world's a complicated place. But somebody's going to make a decision in Washington. It's not clear he can do better than we can when we think through the problem. And the only question is whether there's a better approximation than these perfect notions. Okay. So what I want to do today, or what Chaim and I tried to do, is we wanted to provide a framework for dynamic analysis which allows persistent sources of asymmetric information, which looks harder, but it's going to help me. Okay. What I mean by persistent means you know something that I don't know, and that thing is correlated with what I won't know tomorrow, so you can send signals and do things like that, and it makes sense to do things like that. Okay. So we put restrictions on the way we did it. Okay. We wanted to generate policies that are relatively easy for agents to use. You can still say they're not easy, but they're a lot easier than the Markov perfect strategies. Okay? And they're optimal in some meaningful sense of the world. I can tell you why an agent might actually want to do this. Okay? And in addition, that they're amenable to applied research. So it's going to work out that we're really only partially successful, and I'll tell you what I think the limitations are as we go along. You might point out more. Okay? But there's partial success, so I'm going to try and tell you about it. So what I mean by relatively easy to use, it's got to be less demanding on the agent and less demanding both from a computational point of view, what the agent would have to compute in order to get his optimal policy or the policy, okay? And with respect to the information access and retention that the agent would have to hold to do those computations, okay? Then perfect Bayesian Nash conditions. If you don't know what that is, I'll explain it when I get there, okay? But that's been the typical set of conditions used in the theory literature. Okay, and what I mean by amenable to applied research is equilibrium conditions are defined in terms of observable magnitudes. So at least in principle, I could test them. In principle, we have a chance of that, and it generates policies which can be computed with relative ease. And what I mean by relative ease is they don't exhibit the curse of dimensionality, which is probably familiar to the computer scientists in this room. Okay. Okay, so let me give you some ideas of how complicated this can get. So there's a lot of markets that we try and analyze, okay, where demand is dynamic as well as the production, as well as an investment game. The demand itself is dynamic. So all of those are examples. Network goods are dear to your heart. The one that I would usually use as an example is durable goods. So think about the market for autos for a second. Okay, so there are two classes of agents. There are producers and there are consumers. Each one is dynamic because if I buy something, it lasts till tomorrow. Okay, so what a producer would have to do to choose whatever he's choosing, either price, okay, say just price, okay, is he would have to, if it was going to be a perfect solution, he'd have to know how the consumers respond to that price. Okay, so in order to know how the consumers would respond to that price, I'd have to know each consumer's holding of cars, because it would depend on what cars he has today, and crossed with his demographic characteristics. Okay, because maybe the kid's leaving home, maybe there's 3 kids in the family, maybe there's 2 kids in the family. Okay, and the consumer would have to make a choice for each consumer would know these same things, but would also know the prices and characteristics of goods in the future. Okay, because the distribution of prices and characteristics in the goods in the future given today. Okay, so to actually compute this, we would have what's called a doubly nested fixed point. So each consumer, there'd be a set of prices. Say it's only prices. The characteristics are the same. There'd be a set of prices. The consumers would each take these set of prices and maximize their value function, their current returns, and their continuation values. Okay, that would lead to a set of answers. Okay, for what consumers would do. Then producers would have to check, okay, if that was in fact the prices that they used was in fact was optimal given what the consumers did. Okay, they would then have to recompute the prices, and it would have to go back and forth. So if you think of and that's without choosing characteristics of cars. Okay, this is just choosing the prices. Okay, if you think of what the computational burden of that, it's not going to be within. You couldn't compute it in 20 years with the best computer running today, okay? It's that kind of order of magnitude. So maybe we're doing an approximation which is the wrong kind of approximation. I mean, we just took them straight from theory, okay, when we started doing this stuff, okay? So another way of looking at this, maybe it's reasonable to assume other things, okay? So maybe it's reasonable to assume that consumers and producers have different information sets, okay, that they can only condition on certain things. So the consumer, he might know his car and his needs, and he might know something about the evolution of prices over time. Okay? And the producer would typically know more than that. He'd know costs. And by the way, many producers actually have surveys of consumers, so they don't have the whole distribution, but they have a fair amount of data. General Motors, who gave us their data, had 64,000 consumers every year they go after, and they new car buyers, okay? Just so they can have the information to do the kind of things they want. But neither of these groups will have the information on all the relevant state variables. And instead of assuming the Markov perfect solution, what happens if we just assume agents maximize conditional on their own different, possibly different information sets? What would happen in such a situation? That's the kind of question we're going to ask. Okay. So the one we're going to do today, by the way, is not that complicated because I would never get through it. We have done that one in a small game. I'm going to do a dynamic game between produce. I'm going to carry along an example because it's always easier to do stuff like that. And I'm going to do a dynamic game between producers where there's persistent sources of asymmetric information on the producers, on your competitors' costs. Okay. So the example I'm going to use is deregulated electric utility markets, okay, where each firm owns a set of generators and bids in. They're generated into this independent system operator who then sums all the bids. It's a supply function they bid in. They sum all the bids, intersect it with demand, set a price, and then send quantities out. Okay, that's what's going on. And this is a kind of market where I don't know your costs, okay? If I think you're not going to be in this period, you're not going to bid in because you're going to go down for maintenance, okay, I earn a lot of money because the price will go up along the cost curve, okay? So that's the nature of the game. And then we got to this,
persistent here?
the costs that I don't observe. I don't know your generator's costs, and they're going to be persistent over time, okay? They're not going to be exactly persistent, but they're going to evolve stochastically over time, okay? So we got to this because of what happened in California 3 or 4 years ago when we were starting this project. Okay, so in California, when the prices went through the roof, and if you remember this, it was about 3 or 4 years ago. Okay, they went back, and most of the work on this market has been on the bidding functions, the actual functions bid in. And then they went back and said, what happened when prices went through the roof? Everybody, all of a sudden, it was 104 degrees outside, and everybody stopped bidding in. They bid in one generator and kept the other generator out, okay, and prices went through the roof, okay. And the reason people hadn't analyzed this was just because it's a dynamic game. It's not a static bidding game. It becomes because they have to do maintenance sometimes, okay. So and the only question is when they do maintenance. There's been regulations put in now on this, but go ahead.
So but the cost levels, I mean, you said they evolve stochastically, right? So
Yeah.
you don't fully ever learn the cost of your competitors.
I'm going to come back to that. Okay, so I'm going to give you details on that. Okay, it's going to work out. Oh, you'll see. I'll need something. Okay. Okay, we've also done these other examples. Okay, so testability. When I say it rules out conditions that are formulated in terms of Bayesian posteriors. I never see a Bayesian posterior. Okay, and I'm an empirical guy. I want to be able to test things. Okay, so I'm going to use conditions that are based on consistency of behavior with observed outcomes. Okay, those are going to be my equilibrium conditions. Okay, it's very similar to, I didn't know this, we didn't know this for a while, but it actually ends up being similar to what Fudenberg and Levine called self-confirming equilibria, except for they do it with respect the self-confirming that they actually had the right perceptions, okay, is with respect to behavior of others, of their competitors. And we're going to do it with the right perception, in equilibrium, the right perceptions of outcomes, okay? Because we observe outcomes, or we might observe outcomes, okay? So there's a limitation in this kind of, here's a couple of limitations. It's going to have to be consistent with observed outcomes, so it's only likely to provide an adequate approximation to behavior when the returns from your possible actions can be learnt from previous play. Because I have to, I've got to think of what the guy's doing, okay? And if, in fact, I can learn from the previous play what outcomes were, then it may be reasonable for me to assume that he's actually doing this, okay? So, I'm going to give you a learning rule, which is going to be more familiar to you than to the usual economic audience because it'll be a reinforcement learning type rule, which will actually bring you to these policies. So I can tell you how they would get to such policies, okay? But that doesn't restrict behavior without either something on the prior or repeated play. Okay, so if you're starting something new, we don't have a lot of stuff. Okay, and the other limitation is going to come back to the point that Marcus raised, which is the returns are going to differ with the state. That is, the state, the variables that determine the profits of all these firms. Okay, and the states are going to evolve over time. Okay, and I'm going to have to learn from outcomes on each state. So I'm going to need a finite state space to make this work. Okay, I'm going to need just a finite number of states, which gets back to your point. Okay, and I'll show you how I'll get that in a second. Okay. Okay, so here's the structure of the game.
Do you know if what you get out of that, in the limit of a larger number of states, would approach what you would get in a game with an infinite number of states?
So that's a good question. So I think the question is the following. So if I could keep all of the history in memory, instead of a finite number of history, I did optimal play against the whole, you could have your strategy as a function of the whole history, and I just played finite, okay? Would I do well? So there's one answer in the literature, but it's not satisfactory, and the answer is I can give you bounds for a given game, okay, on how much worse you would do, okay, doing it with a finite number of states than for an infinite number of states. The problem is that those bounds condition on everybody else playing infinite numbers of states. Okay, and so people are working on this now. And the other way of looking at this is...
Because if it does converge, then it's just yet another approximation.
Yes.
And if it doesn't converge, then you're going to land up the wrong equilibrium.
If the other equilibrium is what they're playing. I might have a bit... Yes.
Is what you're playing, right?
Yeah.
Right.
So I have friends who know more mathematics than me who think and are trying to solve this to show exactly that if you do a Markov if you do a game like this with enough history for a capital T I can find epsilon, for every epsilon I can find a capital T such the supremum of the difference in policies. Right? Okay, this is not I'm not doing this, there are other people doing it. Okay, so here's the profit function. My profits, I, depend on my state variable, omega it, my competitor's state variable, omega minus it, my control, which I'm going to call MIT, my competitor's control, M minus IT, and DT, which is some aggregate state. So in the electric utility example, I'm going to need that because weekend and weekdays have different demand. Okay, DT is going to be that. Okay, the omegas are what I don't know how familiar are what econometricians or IO guys generally call, or what Maskin and Tirole call payoff relevant states. So they determine either somebody's demand or somebody's cost. Okay? I'm going to keep to the simple case where M is a control which has a finite support. But I can do this with continuous controls also. Okay, it's just easier to illustrate what's going on. Okay? Okay.
So in the case of the generators, what will be these variables?
I'm going to show you in a second. Okay? So omega it is going to evolve over time. I'm going to keep the example, but I'm going to show you where things get a little more complicated by keeping the general. When I actually do details, I'll do the example. But so omega it evolves over time. So the distribution of omega tomorrow depends on omega today, my control today, and possibly your control today. Okay? So that's just a family of Markov processes. Okay? Controlled Markov processes. Okay. So here's the electricity example that I'm going to carry along, and we've computed the equilibrium for. There's two firms. Each firm has a vector of generators. Okay. The firm's decision is just going to be either I bid a supply function or I go down this period. Okay. If I go down this period, I have an option. I can either do maintenance, okay, or not do maintenance, or just go down. Okay. If I do maintenance, I go back to a starting cost level. It's like putting in a new engine into something, okay? You go back to the starting cost level with a new engine and you start again, okay? If I don't do maintenance, okay, and I am up, then the omega evolves over time stochastically. My cost goes up with use. And it goes up stochastically depending on what happens, okay? So that, and nobody observes it except for you, okay? So omega is a vector of cost of producing electricity on each of the firm's generators, okay? And the cost increases stochastically with use. So the control, which I get one control for each generator, okay? If it's 0, I shut down without doing maintenance. I just shut it down, keep it shut down, okay? This is what happened in California.
And then when you come back, so they're just playing with the supply, and they come back to the old omega,
Yeah.
or to the old distribution.
Yes, they come back to some starting omega. Okay, you put in a new machine. If you go,
No,
no,
without
no, with
maintenance.
0, you come back. You don't. Nothing happens. Next year period, you start with the same omega you started with this
Same,
period
right.
because you didn't do anything. Okay.
That's it.
If you do 1, you do a shutdown and you do maintenance. Then you come back at this fixed omega bar. Okay. And if you do 2, you bid in your market, and omega evolves stochastically over time. It's going to get worse, but in a stochastic way. Okay, it need not get worse. Could stay the same, but it's going to, okay. Okay. So BMI is just the bid function. And this is really simple. So you always bid the same thing. By the way, the interesting thing about the data on this stuff is they don't have to bid the same every day, but they typically do. If they're bidding the generator, the amount of variance in the bid functions is very small. That surprised me because you could think that.
With this, how much you charge for unit of electricity or something?
It's a whole supply curve. So it says, I'll do 20 megawatts at $40 a megawatt and 30 megawatts at $50 a megawatt. It's got to be increasing. That's what they bid in. That's in fact what they do bid in. Okay. Okay. And then there's this independent system operator who has a computer program which sums them all and then gives them back in real time. Then there's stuff to fix up
So
on
it's
something.
just proof that it's computationally difficult because they didn't even try to vary it, right? They just went with the same thing every time, right? It's kind of
Proof. I don't know.
experimental
It's proof. I don't know what proof
Experimental,
means.
Yeah, no, here it's in the experimentalist
Okay.
sense of
Yeah.
the
So
very crude experimentalist sense of proof.
So if a D is a state of demand, this is going to be weekday, weekend stuff. F is the maintenance cost. So maintenance is like investment in this game. Okay? And then the price is just a function of my bids, a function of my competitors' bids, and demand. Similarly, the quantity that goes to each thing is a function of my bid, my competitor's bid, and demand. So the profits are just, there's this price that's set by the ISO. The QIRT is this guy I, this firm I has these R generators. These are the quantities that got allocated. So its revenues are PT times the sum of the quantities. Okay. Then it has the costs for producing those quantities on each of its generators. And then there's maintenance costs if it does go down for maintenance. Okay, and that's the current profits. Okay? That's it. And so that I can write as a function of just my omega I, my control, and then this vector bid functions of the competitors, and the demand of the day. Okay? So in this simple game, B is the only signal sent, right? Because your bid last period tells me something about the state of your cost last period, okay? And your state of your cost last period are correlated with the state of cost this year. Okay, so that I will take into account whether you bid last period, last several periods actually.
You can actually observe the bids?
Yeah, you can observe whether the guy bid in or not.
So they can all observe each other's bids.
Yes, post facto, after it was bid in.
Yes.
Okay? Okay, so the case we're going to do today
They all
is,
have the same evolution, though, right?
I'm going to show you the evolution in a second.
But
Yeah, they're
all
going to.
evolving according
Yeah.
to the same stochastic
Yes,
process.
yes. I don't think that's necessary, but it is going to be that way today. Okay?
Because they might, if they were evolving according to different stochastic processes, then they might not know each other's stochastic process.
Right.
So then, in order to calculate something, they would need, although your equations would probably go through because it's all linear,
Right.
they would need to sample to get something about the other guy's stochastic process. Whereas here, if they know the stochastic process and they're seeing the bids, they don't need to.
So what's going to happen here, let me just say, the equilibrium, I'm going to give you 2 equilibrium conditions.
Uh-huh.
Okay. In one equilibrium condition, they don't need to know the primitives of the other guy. And in the other, they will. Okay. One is going to be a more restricted equilibrium than the other. Okay? But I'm not there yet.
You're not there yet.
Okay? So the main restriction I want to make on here is I'm going to make what we call in economics a capital accumulation game. Capital accumulation games are that the evolution of my own state just depends on my control and my own omega, okay, which would be the case in this game, okay? It doesn't depend on everybody else's control, okay? So that's going to be true in this game. It just depends whether I turn it on or not, okay? But if you were doing an auction, for example, a dynamic auction, dynamic procurement auction, you know, dynamic procurement auction, typically what happens, think about a timber auction. The aggressiveness of the players in this game will depend on how much timber they have to harvest because they own already these lumber facilities, okay? And so an important state variable will be the open capacity coming into the period, okay? And then the open capacity next period, given the open capacity this period, depends on your bid as well as my bid because you might have won the auction, okay? So there is a distinction here.
Because it'll change your supply.
Yes. It will change what I get, so it'll change my open capacity for the next period. So just one second. So let me just say, I'm just going to do the simple capital accumulation games. We can do both, but it gets actually somewhat more complicated. So it would take me longer. You have a question?
So in this, the costs aren't dependent on. So for example, if you turn on a generator, it doesn't matter how much you use it. Like the cost of using it in the future doesn't depend on like
how intensely I use it today.
Yeah.
Yeah, it's not in this game, not in the one I'm going to put up. In general, I think the answer is probably yes. If you get near the cost functions generally go up like this, and if you get near the place where it starts going up, it's more likely that something wrong is going to happen.
So does that happen
in real data?
Yeah.
Yeah. Okay, but it's not going to happen here. Okay. I mean, this is just illustrating what can go on. Okay. Okay, so the state of the game is going to be, so everybody makes decisions based on their information set. That's all they know, so they have to, okay. So the state of the game is going to be the information set of the agents in the game, okay. So JIT is the information set of agent I, okay. And it's going to consist of two types of variables. One variable which is public information, okay, we all know this, and one variable which is private information, one set of variables that is private information, okay? So in the example, okay, the private information are the cost states of the generator, and the public information are all the history of bids. Okay, because I know we see the bids post facto, okay? And you can write down lots of other examples, okay? So this is where this thing comes in. So without further restrictions, all past history is relevant. Okay, why is all past history relevant? So my decision on I'm A, okay, and Marcus is B, and my decision on whether to bid in today depends on what I think Marcus will do today. Because if he doesn't bid and I make a fortune by bidding it. Is that clear? Okay. But Marcus and that will depend on the last time I saw Marcus go down, because if he went down a long time ago, he's probably in a bad cost state. Is that clear? Okay. But Marcus's decision the last time he went down depended on what he thought, he thought I would go down at that time when he went down, okay? And that's going to depend on my cost, on the times before that I went down. How many? Okay, and that's an infinite regress. Yeah. Okay? Okay, so I can't do that. I need a finite state game to play my, okay? So I'm going to assume for now, there are different ways of doing this. So I'm going to take the easiest way out now just to finish what's going on, okay? So I'm going to assume every L periods, a regulator goes around and inspects the machines and gives you a public report, okay? So, it's sort of trivial, but you can prove that then there is an equilibrium with strategies that only depend on the report and the bid since the report, okay?
Sure.
Yeah. Yeah. So let me say there are other ways of doing this, and I'm going to come back to other ways of doing it as I go along. Okay, but let me just do that. Let me just say, even for this simple game, it would be next to impossible to compute a Bayesian perfect equilibrium. Okay, and the way to think about that is any policy I do today, okay, affects my continuation value because it affects what other people think I will do tomorrow. Okay. So what I would have to do is I would have to get equilibrium policies, okay, at the same time as posterior. So your policy and my policy and the right posterior for you all simultaneously for every possible sample path in this thing, and it becomes quickly impossible.
Yeah, so it's like probably super exponential, or at least exponential in L. Right?
Okay, so I'm going to give you a different notion of equilibrium. This is where we call it experience-based equilibrium. You'll see why in a second. Okay, no question. Okay, so I'm going to premise it on the ability of players to learn the value of outcomes from their strategies at states which are visited repeatedly. So if I hit this state many times, I'll eventually work out what the outcomes from that state are. Okay? So equilibrium strategies are going to ensure that at those states, strategies are optimal given participants' evaluations. Okay? And the evaluations are consistent with the empirical distribution of outcomes and the primitives. Okay, so the evaluations I assign for things that are hit, are going to be consistent with the actual empirical distribution, or you can call it, the empirical distribution is the equilibrium distribution.
Does it matter how many, you have to set a threshold for what it means to be visited repeatedly.
Yeah,
right?
so I'm doing theory.
And then how sensitive is it to that threshold?
Right. So let me just say, I'm doing theory now. That's my excuse. And what I'm going to do is show you that, well, I'm going to give you 3 conditions. Now, one of them that is, I'm only going to do conditions that are in the recurrent class. It's going to be a Markov chain, and each point in the recurrent class is going to be hit infinitely often. So in theory, I can get them all in the recurrent class, but not outside. And there's going to be a distinction there. Okay? But there is an empirical issue. There is a real substantive issue, and we're not there.
As you're trying to fit this,
Yeah.
where is your
Yes.
threshold for,
Yes.
because you can't do it infinitely often, so you have to set it at
Right.
something, and what's the sensitivity to where you set it?
That's right.
Yeah.
I'm going to have to do that. Okay? Okay. So this equilibrium, it has 3 objects in it, and then 3 conditions on the 3 objects. Okay? For the equilibrium. Okay? So one is this S is just the possible states. So what are the possible states? The possible information sets for all the agents. Okay? A vector of information sets. So R is going to be a subset of S. Okay? It's going to be all those points that are hit infinitely often. Okay? But it's going to be a recurrent class of a Markov. Okay? So I'm going to need R, and I'm going to need strategies for each information set. Okay? That's going to be another object. So those are standard sort of things for Markov games. Okay? The third thing is new. Okay? So it's these numbers. It's a set of numbers, which should be interpreted as follows. They give me the perceived expected discounted value of current and future net cash flows conditional on a decision. So fix the agent's information set, JI. He can do 3 or 4 different things. So for each information set, there's 3 or 4 of these W's. And what they represent is the expected discounted value of future net cash flows should I play M and I was at JI. Okay, so they're just numbers, and there's going to be equilibrium conditions on those numbers to be equilibrium numbers.
And you say that there are some finite number of those.
There's a finite number of states, and there's going to be a finite number of these,
Right.
so everything's going to be
But
fine.
then another question I would have is, how does that number of states scale as you actually go putting in
More state variables.
yeah, then,
Yeah, I'm going to come to that.
How's that scale?
Okay, that's part of the whole game. Okay, that's part of what it's going to end up not having a curse dimensionality.
I have a much more high level.
Yeah.
So in these in the lumber setting or the like electricity setting, so you said that like a lot of these places submit the same bid. A lot of
Same bidding function. They go down. Yeah.
I mean, so in the like online AdWords stuff, I guess most participants seem to be very dynamic. That they sort of they try different strategies. They're very active about this, and sort of why don't we see more creativity? Maybe I guess this is So one question is why don't we see more creativity?
Maybe they got it right.
One answer would just be that it doesn't actually matter. Another answer would be that there are only 2 companies involved, and they meet over lunch and say, hey, why don't we disagree that we'll do it this way, and we'll both make off like.
So let me just say, you could So your second option, your first option, I don't really have anything to say because I haven't investigated it, whether it matters or not. Okay, there are many companies in this. I've actually looked at the British electric utility market, and there's like 7 major operators and a bunch of small guys. Okay,
Your advertising setting, I guess. Now there are a few big companies that do lots and tons of.
yeah, and then what was your second thing was?
Collusion, basically.
Yeah, collusion. I'm not going to do it here, but you can do these games with collusion. That's one of the reasons we did these games. Okay. Okay. That was one of the examples. I'm just not going over today.
It's not the same players meet again and again and again.
I mean, the people who bid for the word toothpaste. It's probably Crest and other toothpaste.
So these bids, by the way, let me just say.
And as we've had people investigating in the Empirical economics program, the guy from Wisconsin investigated that when you have these people who are bidding against each other, their bids are often being controlled by the same advertising firm. So there's huge amounts of collusion because it's the same firm placing them, and anyway. So that's a real effect.
There is a literature in IO on collusion. Okay, and I've contributed to that literature. So, yeah. But I'm not. And the asymmetric information helps analyze those things. Okay, but I don't want to do it today. Okay, it takes me off.
Why you don't see more creativity in how people are.
I think you were curious too, right?
Yeah.
Why everyone was.
Yeah, no, I told you this because I was surprised. Okay, okay. So here's my conditions on those 3 things. Okay, so R is a recurrent class of the Markov process. So every Markov process on a finite state is going to eventually wander into one recurrent class, and once it's in it, it doesn't exit from it. So it'll be in it with. So if you start a subgame from within it, you'll stay within it forever with probability 1. Okay, and that could be the whole state space, But this is not really an assumption. Okay. Okay. Then the strategies have to be optimal in the sense that the strategies have to maximize with respect to their perceptions. Okay, so that's a standard condition in Markov games. Okay, the new condition is this one. The values that we attach to a state, okay, have to be consistent. So what do I mean by consistent? This is the value I attach to state to playing m star at ji. Okay, it's the expected discounted value of future net cash flow. Okay, what does it consist of? This pi e jim, which is current profits and a continuation value. I'll explain them both. Okay, so the current profits, they are in fact a function of what the other guy does. I don't know what the other guy will do because it's asymmetric information, but there will be a distribution of j minus I given ji in the equilibrium. There will be an empirical distribution of what he does when I have ji. He'll do different things because he has different information sets than I have, okay? But there will be an empirical distribution, and this profit function has to integrate out with respect to that empirical distribution. Okay? Similarly, this is the continuation value. So j prime is where I get to tomorrow, given that I am ji today, and there should be a comma m star here. Then I play m star today. This is a typo. Okay? So there's a distribution of that. And tomorrow I know that wherever I land, I'm going to choose the m star. So this is going to be the continuation value. Okay.
And if you didn't have this, you would argue that there's some opportunity for arbitrage or something that some
you can do better.
Middleman could jump in here and say, let me put in your bids for you and kind of soak up.
Yes, you could always make more money if you didn't do this. Okay? Okay. Okay, is that clear? So these are the conditions of an empirical guy for equilibrium. Okay, because what I did is I substituted for all these complicated animals, these posteriors and everything like that. What I did is I just substituted the empirical distribution of j minus I given ji. What you did, what I saw when I was at this state, what did I see you do? Okay, and there's going to be a distribution of that in the data, and I'm going to integrate out with respect to that. And there's going to be a distribution of where I am tomorrow, given where I am today and playing m star, and I'm going to use that distribution. So this is a sense where I'm an empirical guy in this. Okay. Okay. So let me tell you a few things about the equilibrium. Okay, and some of them are problematic. So beliefs in learning. The good thing for an applied guy like me is beliefs are not on types. okay, because beliefs on types are not observed, okay, and I can't do that, okay, and can't be directly tested, okay, and these are not beliefs on types, they are beliefs on outcomes, okay, and I have a chance of getting outcomes, okay. The outcomes themselves, okay, are the average values generated by equilibrium play and can be learned from repeated play. And I'm going to show you in a minute exactly how they can be learned. I'm going to give you an algorithm that will give you exactly these W's. Okay? We can do it on the computer, and that's how we computed our equilibrium. Okay? But the same algorithm could be used by people to learn what they're doing. Okay? And this implies that I can compute the equilibrium without ever calculating posterior distributions. Okay?
You don't need them.
I just get these W's. I give you
the
this learning algorithm. I get the W's, and I'm finished. Okay? Okay, so
you really do care how stable the W's are to your model because
yes,
to the
W's
assumptions you made in your model, because everything
right.
is, these are your observables, these are your, yeah.
So I'm going to come back a little bit about the empirical problems, okay? So, there's part of the issue is, I always say this as an excuse, but you got to start somewhere. And okay. So let me tell you more about the problem. So this recurrent class has two kinds of points, okay, in them, okay? There are points which we call interior in a separate paper. What are interior points? They're points where no matter what I played, equilibrium or not equilibrium, any feasible thing, I stay in the recurrent class with probability 1.
That is what a physicist would call the single phase regime. No matter what you do, like to the boundary conditions, as we call it, or the initial, there's only one state. So that's where you're going to land up. There's only one stable state. So that's what happens, for example, at high temperature in a magnet. No matter what you do, that's where you land up. Whereas there's a two or more phase regime where what you do on the boundary will affect where you go. So as you pass from one to the other, you're going through a phase transition. Anyway, go on.
Okay.
Okay.
So it's actually very simple because I'm going to tell you what the other kind of points are boundary points. So what's a boundary point to us? A boundary point is you're in a recurrent class. So if you play the optimal thing, by definition, you're staying in the recurrent class with probability 1. That's the definition of the recurrent class.
Right.
Okay. But there may be a feasible thing that you could do which would take you out of the recurrent class. Is that clear? Okay. The only condition I have on those things that would take you out is the inequality that my perception must be such that, okay, I don't want to go there. Is that clear? That's okay. So that's not true in Markov perfect equilibrium. You have many more conditions on it. Okay, that's the weakening. Okay. So what kind of problems does this arise? Okay. So there's in these equilibria, even if I did perfect Bayes, which by the way is a subset of these, so you can show that perfect Bayes satisfies these conditions. Okay. And they admit multiplicity. But now I'm going to have a whole lot more multiplicity. Why? Because with certain perceptions of what happens outside of the boundary, I can support different recurrent classes. If I think it's terrible to go out there and I never try going out there, okay, I'll find a recurrent class that doesn't go out there. Do you know? I mean, is that clear? So you can support a ton of stuff, okay, which is the problem with this. Okay. Okay. So let me tell you what I mean by a problem. Okay, so a problem is the following. There's a multiplicity. The multiplicity does not affect what I can estimate. Okay, I'm not going to do estimation today. That's really what I do most of the time. Okay, but I'm not going to do it today. I can still estimate all the primitives of the model. Okay, with multiplicity or without multiplicity. Okay, and that's going to be true generically in I/O. Okay, that is almost every model that I know I can do that. Okay, I think maybe every, but. The problem is a lot of the reason why we're doing this is so we can do counterfactuals. So the government changes a regulation or, and then I'm in trouble, right? Because if I'm in a counterfactual, I'm doing a counterfactual, I don't know, maybe with the one that we've played before, I can look in the data and find out what the equilibrium was. Okay? But in a counterfactual, the whole idea is, unless a counterfactual brings you back to someplace you were before, it's not there, okay? And you have to supplement this somehow to do that. Okay, that's the real problem with multiplicity. Okay, there are two ways out of it. One is to use the data. Again, that won't work for counterfactuals, but it will work for this. Okay, and the other way is to impose further restrictions on behavior. So this goes back to your question before, and this is now my second equilibrium. Okay, so I'm going to show you what other restrictions I'm going to impose, and it's going to be things like you said you need. Okay. So the experience-based notion, the simple notion, just says this has to be consistent when you play M star. Doesn't have to be consistent when I play an M different than M star. That's just my perception. Is that clear? I never play it, I never learn about it. Okay. So the first question we asked ourselves when we got to here is we said, look, when is it feasible to know that for you to be able to figure out what would happen if you played something you didn't play? Because then I could learn about it. Is that clear? And what would I need to know? I would need to know the profits if I didn't play M. And I need to know the distribution of where I would end up if I didn't play N. Okay? And then I'd have to need to know the continuation values from that point that I would end up at. Is that clear? So it works out that, and I'm not going to do it here, but it works out that in these capital accumulation games, it's going to be possible provided you land in the recurrent class. Okay, so you play M and you land in the recurrent class. That means I can get the continuation values.
Wait, in the recurrent class. So is it one recurrent
You're all
class?
the same recurrent class you started from.
I see. So if you stay, I would think of it if you stay within that phase, and come on, kind of
Yes.
crazy.
Yes.
Right. Then we could do. Okay.
Yeah.
I'm saying if you had two possible options and both of them land you in the recurrent class, then you know both of their.
Yes, you know they'll come. And I would have to. It's not. It's not that simple
And so
because
you
I have
would
to
kind of
know.
need this so that your counterfactuals are not taking you out of the. I mean.
No, I would need. I need this. Well, I'll show you why I need it right
Okay.
now. Okay. What did you? What was your question?
So just wanted to make sure I understand. You're saying that if you have
Yeah, two actions. One you play, one you don't. But the other one would keep you in the recurrent class. You're in business.
You're fine.
Okay, that's this restricted equilibrium. By the way, you can do more than this, as I've started to figure out lately. Okay, but I'm going to just stick with this now. Okay, you can do some things that aren't in the recurrent class, at least inequality-wise. Okay. So what the restricted EBE says, look, I'm going to now define expected profits if I play any M, not the M star. Okay? And those expectations are going to assume that when I'm at this JI, you still play the same J minus I, I'm going to use the same equilibrium distribution to integrate out, but I can compute the profits if I play M and you play the same thing you used to play, okay, at that JI. Okay? And the same thing for my PJ prime given JI and M. Okay? I can be able to compute that. Okay? I can tell you where I would be in the future if I would have played a different M. Is that clear? If you kept playing the same ones you were playing before at the state that I observed.
So you're almost like self-consistently defining your state by the W's which keep you in
The recurrent
that
class.
state.
Yeah.
Do you know that something that looks remarkably like this, it's called the Debruchin-Langford-Ruel conditions from the 1960s in physics, defining how phases react by keeping you inside the state. So it's actually really interesting with conditional probabilities like this. So anyway,
It's amazing
tell you
how
about
much.
the DLR conditions after the talk.
After the talk, I'll tell you how I got to the stochastic algorithm stuff first, and then found out that Robinson and Rowe had done it all 40 years, 60 years ago. Go ahead.
Let me see if I'm interpreting this correctly. If I take an action that takes us outside the recurrent state, there's
Current
some
class.
monitoring, recurrent class, there's some monitoring issues here, but you may observe, at least with some probability, that I did this thing which was off the equilibrium path. But I am evaluating my continuation paths as if I believe that nobody will react to that and everyone will continue
Good.
playing.
So can
as
I?
they do.
That's good. Good
Is
point.
that correct?
Yeah. Currently, let me just say the other way of doing this, okay, which we've been working on for the empirical work, okay, is the way I'm going to do the restriction is the following. Okay, I'm going to restrict it so that I'll be able to evaluate an alternative. Okay, if by playing that alternative in the recurrent class, if by playing that alternative you wouldn't know that I played an alternative strategy. That is, there's an alternative set of private information, which with this public information would make me do it. I'm not there, okay? But I can evaluate what would happen if I played that, because I know what you would do in response to that. Okay, so we're doing. So there's a separate paper I'm in the middle of doing.
That gets you at least somewhat past the.
Yes, it does get. So I said there's more. You could do more. Okay, and I'm not exactly sure of the limitations. Okay, and I am working on it. Maybe if you have me some other time, I'll get it.
This is going to sound like a criticism. It's not really a criticism because math is tautological, but what you're doing is somewhat tautological in the sense that the equations that you're writing down to specify the restrictions are telling you, in a sense, that your state is characterized by the W's. I mean, this is a self-consistency which tells you that you can characterize the recurrent state by the W's.
That's right.
And so you're asking, in a sense, when can I use the W's? And then you are saying I can use the W's in cases in which I can characterize my recurrent states by my W's.
Yeah. So it is.
No.
But just let me.
PLR did something similar, so it's not, and it turned out to be very useful. So it's not the criticism that it sounds like, but you see what I'm
I
saying,
do see
right?
what. So let me.
Because you had a similar equation in terms of things which were characterizing your state.
Right, but
you now say let the W's. Let me look at the cases in which I can write a similar kind of equation for my W's.
So let me just two things. One, if I knew the W's, that's it. The game's over. Okay. The second thing is you got to remember I can learn these W's. I'm now going to show you how to learn the W's from the primitives, so that they are in fact consistent. That's the algorithm. So that's where I go next. Okay. Okay.
It sounds like Jennifer was saying that W is a sufficient statistic for what state you're in, but
the set of W. No, it's not true. It's not true.
But if W satisfies this, then I can define my state via the set of conditionals with the W's with.
But you need the condition probability.
Yeah, you need the conditional probability.
And of course you need the primitive. Piece. Yeah, of course you do.
That's
because
right.
How could you define anything without the piece? But that it's but he's looking at the case in which he gets self-consistency with the W's and says, in a sense, I can do this. There was a problem if he got taken out of the state, and now he's saying, if I look at a restriction in which the W's keep me in the state with any of those conditional probabilities, then I can look at things in terms of the W's.
That's right.
Right?
Right.
So
but it is true that to characterize it, I need the distribution.
Yeah. Well, otherwise.
Okay. I'm going to quit the bounded finite state space condition. I'm going to go over it quickly, but let me just say there are different ways to do it by getting primitives that work to give you a finite state space, and then there's another way of doing it, which is you could assume people have bounded cognitive abilities, okay, and just say they can only keep so much in memory. And when we do the computation, I'm going to compare these two. So I'm going to say, I'm going to get a full equilibrium, and then I'm going to say, what would happen if you just kept a little bit in memory and not everything, and how different are the computational problems? Okay. So, I'm not going to go over the ways I get to the full equilibrium. Okay. You can look in the paper. There's lots. Okay. I'm going to tell you how to compute this. I have this funny feeling that there are many people in the audience who know more about this than me, but I will give you a brief resume, and if I'm going too slow or too fast, you should tell me. So this is just a reinforcement learning algorithm, but just applied to a dynamic game. Okay. So, and as a result, as all reinforcement learning algorithms are, you could say that they're approximating a learning process. That's what they're doing. Okay, so the iterations. So it's going to be an iterative procedure. So I start somewhere, I do something. Okay, I go somewhere else, I put something in memory, bring something back out, and do it again. Okay, until I get to an equilibrium condition. So I need a location where I am now. So K is going to index iterations for me. L is going to be my location. And it's going to be the information sets of the various agents. Okay, because that's the state space. Okay. I'm going to need stuff in memory. Okay, that I'm going to update with each iteration, okay? So it's going to be these perceived evaluations, WK. Well, I'm going to start with some, and then I'm going to update them, okay? And then just the number of times I visited the point, because the precision of the estimate will depend on the number of times I visited the point, okay? So the algorithm, the iterative algorithm has to update the location, the W's, and the H's, okay? And I'm going to give you an iteration, and I'm going to give you a criteria for convergence to an equilibrium, okay? I'm going to skip parts of this. So the way you do this, there are two aspects to the computational burden. One is just the computation at each time I'm at a location. And one is, and the bigger one is, going down, again, it's going to be what's called an asynchronous algorithm. So I only update one point at a time, okay? And what's going to happen is I'm going to get to a point, then I have to go down through the memory and find the stuff that's at that point and bring it back up. And that's the real computational burden of this stuff, okay? Because it can get to be lots of stuff down there, okay? And there are different ways of doing this, and I'm not going to, of doing the memory, so it's more efficient or less efficient.
There might be other kinds of algorithms, like leaf propagation algorithms or something that could be doing it in a more parallel fashion.
I'm sure parallel for sure.
Yeah.
This is not my forte. I'm sure there are people that there are better ways of doing this than, because it just isn't, it's not something I've ever studied, okay? Okay, so I'm going to tell you how it works, okay? First of all, I'm going to update the location. So the way, it's pretty easy. It's a very simple algorithm, other than the memory stuff, okay? So I'm at location LK. For each agent, there's these W's in memory that I bring up, and I choose the M that maximizes, what the OR guys call the greedy policy, okay? The one that maximizes, okay? So I do that for each agent, okay? Then, given everybody's policies, there's a random outcome. And I just take a random draw from the random number generator for those outcomes, okay? And I get the new location. I just put everybody goes somewhere, I get the new location, that's now in memory, okay? So that's updating the location. Okay, now I have to tell you how I'm going to update the values, the W's, okay? So this is a little bit different. In this game, Bm minus I is the observed thing, okay? So I'm going to write down an equation for what an economist would call the actual value function, okay, if I had perceptions of W, of the W in memory, okay? So what would be the value function, okay, ex post, realized, okay? When I go into this period, I don't know what the other guy's going to play. But ex post, I saw what I did see. Okay? Ex post, I can calculate what value I would have gotten had I played different M's. Because I just put in the other guy's Bm minus I. Okay? And I can tell you where I would have gotten, JK. Okay? So this is current profits, and this is continuation value. So this is the actual realized value. It's not really a value because the guy didn't know it, but it's post facto what the realized perception of the realized value would have been. Okay? Okay, and then what I'm going to do is with these W's, what are these W's? Remember, in equilibrium, what these W's are is they're the expectation of these realized values. They're the expected discounted values. Is that clear? Okay, so the way I'm going to update WK plus 1 minus WK, is the difference between this realized value and what I expected for it, which is my perception for the expected discounted value that's sitting in memory.
Now, HK is the number of times it was visited.
Yeah.
Isn't that a random variable?
So I keep it in memory. So let me just say.
But aren't you like dividing, is it kosher to divide through by a random variable?
So
instead,
because
you're looking at expectations.
It's a Markov process.
Oh, good.
Okay, so this is just an averaging process. If H was the number of times I hit this point by iteration K, this would be 1 over those number of times. This would be n minus 1 over n the number of the times, and it would just be an average. Okay, this is very simple. Think of what you would have to do if you were actually integrating out over the future, over the possible states that could happen in the future. Okay, all you do here is you do a simple average. Okay. Okay, the thing to realize, of course, is if we're at the optimal thing, then the expectation of this is this. Okay, and it will tend to stop there. Okay? A couple other things. The optimal weights, by the way, aren't the 1 over n number of times you hit. What you really want to do is you want to downweight the earlier observations because they're more noisy than the later observations. And there's a whole literature on optimal weights, which I'm not going to go into here, okay, for Robinson-Monroe type processes, okay? These do satisfy the Robinson-Monroe conditions for convergence in a single agent game, okay? Okay, so the computational properties, much of this was done before in an old paper I have in Econometrica. You can't prove this will converge. You keep doing this algorithm, you can't prove it's going to converge. It need not converge, okay?
Do you have examples where it doesn't converge, or you just can't prove that it does converge?
Well, the only ones I don't have examples, but I can't prove. Actually, its convergent properties are much better than most of the symmetric Markov perfect things that I have computed, because the stochasticness gives you an averaging process, which makes it work better. But I can't prove it, and I know that Britsaikis and Sekilis have tried, and they didn't do it, so I sort of gave up. The one that you can prove for these kind of games are zero-sum games, because they transfer into a min-max problem, and then it's a single agent problem, and then you can use contraction mapping properties to. Okay, but regardless of that, I can test whether I've converged, because I can look at the left-hand side and see if it equals the right-hand side. Okay, and I'm going to show you how to do that in an efficient way. Okay, but the properties algorithm, what makes it nice, okay, is this asynchronous part of it, that I only update one thing at a time. So think of what you do when you update a value function and sort of it's, okay. What you do is you take all the points one at a time. You update every point, every iteration. Okay, so you take all, and then at each point you integrate out over the future. There's two curses dimensionality there. There's the number of states that I have to update. Okay, and then there's this integral of the future, which can involve a lot of different things. Okay, and in fact you can prove that there's these two cursive dimensions. Okay, so this algorithm is asynchronous, and it's going to wander into this recurrent class, and once it's there, it stays there. And the recurrent class doesn't have to be any particular relationship to the number of states. Okay?
And how do we know it wanders into the recurrent class?
Any Markov process will wander in. I'm going to show you how to test for it in a second. Okay? I'm going to show you how to test if this recurrent class and these W's are in fact in equilibrium. Okay? That's a different issue. So that's one thing. So it gets rid of this. Let me just say it is true that I've tried this on symmetric information games quite a bit. And it is true that, that as I get more state variables, it gets bigger, but it gets bigger linearly, not exponentially or geometrically, and that's a huge difference. In applied work, you can do a lot more, because the difference between geometric and linear is just huge. Okay, when you get to large dimensions, and so you really can do a lot more with this. And then the other place where the cursive dimensionality comes in is if you're going to integrate over all the states you can be in the future. But now it doesn't matter how many states you do. All you're doing is an averaging process. You're taking two numbers and putting them together. That's it. So that goes away entirely.
But the size of your recurrent class doesn't increase exponentially either?
No, it increases linearly. Okay. I mean, I don't have a rule for that. And I know examples where it doesn't increase at all.
You've observed that.
Yeah, I observed that. It can increase in any different way. The way to think about this go ahead. I won't go that way. Go ahead.
So it seems like another way to think about getting rid of the cursive dimensionality would be to use some heuristic to sort of just calculate these sort of transition probabilities empirically, and then say which of these are the recurrent states, which are the ones that I visited a lot, and then do the stochastic integration, update your value function just within that class of states where you have only a relatively small number of states. So should I think of the advantage of this method as being that you don't need to have a rule for figuring out which are in the recurrent class?
Yes. You don't know what's in the recurrent class until you compute it. Okay. I mean, if you saw data, it's different. If I had data and I was working from data, it's different. But yeah.
Yeah. Well, but I mean, so with this algorithm, you're not going to end up knowing what R is any more than
Yeah, you will.
The other method, right?
You will. I'll show you how to compute it in a second.
you have an intuition for the linearity of that? Because I'm just thinking, like, if you double the number of generators, then in some sense.
So here's the way to think about it. So I remember, I'll tell you the one I did. Okay, I worked for a long time in the auto industry. You know that. Okay, and we were doing stuff on miles per gallon because of CAFE standards and stuff like that. And the question is, what would happen, if we put in different standards? Okay, so the two major state variables were for each car were the size of the car and the miles per gallon of the car, and the cost function depended on the size and the miles per gallon. Okay, so what happened in the equilibrium is that nobody wanted to buy a small car that had low miles per gallon, so it wasn't in the recurrent class. It wasn't profitable ever to produce it. Is that clear? And it was too costly, okay, to have a big car with a high miles per gallon. So that wasn't in the recurrent class. It wasn't profitable. So the profitability of the thing just limited the thing to be a very narrow range of cars along a line. Mm-hmm. And that's going to end up being the recurrent class. Another way of thinking about it, the other kinds of stuff we do is, we go bigger and bigger markets. So it's true, bigger markets can support more firms. But you never get back to the place where there's a small number of firms, because before you get back there, there's entry.
So for example, in the case of the generators, wouldn't be the case that if you double the number of generators, that one of them would have uniformly low cost and the other one's all high cost because they just couldn't compete. I mean,
then they drop out.
They would drop out.
Yeah, that's the kind of argument that leads to the recurrent class. I mean, and it's different for every different. You set it up, and whatever you put into the primitives is going to determine what's in the recurrent class, and it's going to be the economics of the problem that's going to determine that. Yeah.
Just wondering, does this always converge to the same thing?
No.
It seems like if you.
No, I'm going to get to that. I'm going to get to that. I promise to get that. No. So what? I already told you there's a multiple equilibrium. Okay. Okay. So depending on the way I say it converges. Okay. I can give you a test for whether. Okay. It need not always converge to the same place. Okay. What's going to determine where it converges? Okay. Is a lot. Is going to be the starting values. Okay. And then something about how you program the thing to do it. Okay. If you start all options at very high starting values, okay, every W is very high, way higher than you know it is, you're going to explore everything along the way down. You start everything way higher than they are. You'll choose one that's the highest. You'll keep doing it. It's going to go down. Is that clear? At some point, some other one will come up, and it will go down. And if you try them all, if you start at a very high value, you're going to explore almost everything. Okay? That's okay. This is well known in the OR literature that you should be doing this. I mean, if you want to get something that has explored sufficiently. Okay, so that's that. So I've got to tell you how to test for the equilibrium, and then I'll go back to the I/O stuff. By the way, anybody who has questions, you should keep going, because I'm sort of getting to the end, even though I didn't think I would. So, okay, so I want to test. I've run this thing 100 million times, 100 million iterations or whatever, and I'm going to stop it and test, am I at an equilibrium? Okay, that's the goal. Okay, so I need a candidate for the recurrent class. Okay, I need to show that the policies are optimal, given the W's, and I got to see the consistency of the W's. Those are the three conditions that I have to show. Okay, so the candidate for the recurrent class is pretty easy. You start at any S0. Okay, you simulate J1 periods and then add another J2 periods. Okay, you look at the difference between J2 and the states that were hit between J1 and J2. If J1 and J2 go off to infinity, you'll get a recurrent class because of the Markov process. The way you do this empirically is you go from J1 to J2, and then you go from J2 to 2J2, and you see if between J2 and 2J2 they're the same as J2 and J1. Okay, that's essentially what you do in the computer. Okay, in the computer algorithm. Okay, so that's easy. The optimality of policies is for that W is guaranteed by the way you're calculating the M's. You're calculating the maximum M. Okay, so the hard condition is this consistency condition. Okay, so it's that I've got to be ensured that when I use this W, is that clear? I actually get pi EJA and I get the right things. Okay. So that looks like an easy thing, but direct summation of this puts you back into the curse of dimensionality. Okay. So there's this paper in Econometrica by Paul McGuire and myself that did this for symmetric information game. I tell you this not because I want to tell you about the paper, but and what happened is, I forget exactly the numbers, but to compute 100 million draws, it took us something like an hour or two. And then to do the test, by the time we were at 12 firm equilibria, to do the test took us 3 days for the 100 million. So it grows. It's a huge difference when it grows, Jim. Okay. So you want to get around this problem. So that's what I'm going to tell you how to do. So here's how I'm going to do it. I'm going to do it by simulation, just like I did everything else by simulation. I'm going to start at some S0 that's in this candidate recurrent class that I have. Okay? And I'm going to forward simulate. Okay? So just like I did in the algorithm. Okay? Each time I hit a point, I have an I get this V from that point, which was the realized continuation value. Okay? I'm going to come back to this point again because it's in the recurrent class. I'll get another estimate of this V. And I'm going to accumulate them. I get my U, which is my mean at this state, and this Ji. And I also get a variance at this state and this Ji. Is that clear? Because I hit this point many times. So I get a mean at that point, and I get a variance at that point. Okay. I'm going to let E be the expectation operator that takes expectations over simulated draws. Okay. And let me just do a location, a particular Ji. It works for all locations. Okay. I'm going to use the soup norm. Okay, so I'm going to define this tau L. Okay, what's tau L? It's the difference between my average that I've got in my data now from this simulation run and the W I started out with, which, remember, is supposed to be the expected discounted value of future net cash flows. Okay, and I'm going to normalize by W to put a percentage. Okay? And I'm going to take, so what's the expectation of that tau L? Okay? Well, I can always divide it into two terms, the difference between U and its expectation, and this between its expectation and the actual W. Okay? The first is the variance when I square it, and the second is the bias. Because remember, U is supposed to be estimating W. So EU should be W if I'm at an equilibrium. Okay? But I have this variance term there also. Okay? But now what I do is I run this many times. I have many states, okay? And FL is a distribution of the fraction of draws that hit this state L. It's just, I hit this point many times, and there's going to be 100,000 points. Each point gets a probability. That's what these FLs are. They're empirical probabilities, okay? So what do I know? I know from the law of large numbers that the average estimate of the sigma squares, okay, is going to converge to the average of UWL minus this. I never see sigma squared. I know the expectation of this is the variance plus the bias. I don't know the variance and I don't know the bias. All I know is this number, tau L, I can calculate. Is that clear? Okay? So I don't know the variance, I don't know the bias. So my problem is, okay, but I have a sampling estimate of the variance for each point. And the average of the variances is going to, by the law of large number, go to the true average of the variances. So this difference is going to go to 0. So when I take the average of the tau L's and I take away this difference, I get the average of the biases, which is the soup norm in L squared PR norm in the right probability distribution, the probability in the invariant measure over this Markov process. Okay, so that's easy. That takes 10, 15 minutes on the computer, okay, rather than 3 days, 4 days, okay?
So you're not kind of computing these, you're sampling kind of.
I'm sampling, but I'm going to eventually hit every point, right?
Yes.
And I'm going to every point in the recurrent class.
Right,
Okay, so now I'm going to come back to my example and compute my example. Is that okay? Again, anybody wants to stop with a question or comment, that's fine. Okay, so here's my example. So I'm going to ask a bunch of, first of all ask some computational problems, and I'm going to ask some economic questions, okay? So these are my questions. Does the impact of increasing the number of periods of memory before full revelation taper off? This is your question, okay? So I'm going to do it for 4, 5, 6 periods of memory, and let's see if 6 is with 5, okay? For a full equilibrium,
yes.
Okay? Then do reasonable bounds, so these are full equilibria. Then I'm going to put bounds on the memory. I'm not going to do a full equilibria. I'm going to ask the same question. Okay, do the bounds make me get to different policies, different values, and stuff like that?
Right, and that's what you said your friend was doing.
Yes.
Also trying to prove with the epsilons and the
Yes.
T's and the, right, and you're observing that and seeing.
The friend is Gabriel Weintraub in the OR department at Columbia.
Okay.
And I'm going to then I'm going to compare the computational burden of the experience-based equilibrium to a full information equilibrium, okay? Because that's what everybody's been using, only because they thought it was impossible to do. And I don't think people think that everybody knows everything. Okay, it was just the easiest thing to do. And again, you don't blame people. People have to do something, right? I mean, somebody's going to make decisions. Okay, and then the electric utility questions I'm going to ask is the asymmetric information? I'm going to compare the asymmetric information problem to the social planner problems. What's the incentive in a world of competing electric utilities, okay, generators? Compared to what a social planner would do, and also compared to what a full information equilibrium would do. Okay? Okay. And then in the end, I'm going to show you, so this I wasn't going to do, but it works out that for different primitives, the answers to these questions are different. So they were sort of interesting. So I'll tell you, we got one empirical, sort of empirical-ish answer out of this. Okay? This is a model. There's two kinds of generators, two firms. They each own different kinds of generators. There's a big firm. The big firm has two generators. They're coal-fired generators. So they have lower. So the big firm has coal-fired generators. The small firm has gas generators. This is true in the industry, by the way. The coal-fired generators have lower marginal cost than the gas-fired generators. They're usually bigger, okay, but they have higher startup costs. So you'll often see the gas-fired generators are often things as small as a jet engine that they'll just bring up at times when there's excess peak load stuff. Okay. So that's a setup. The elasticity of demand, it's small and very inelastic demand we program because that's the way electricity demand is. It's very inelastic. Okay. The initial conditions. Again, we wanted to start with initial conditions that were very much higher than we thought the answer was, so that we would explore everything. Okay, this is the answer that somebody asked me this question before. So for expected profits, we say, what would be the profits if you bid your MI and the other guy didn't bid anything? That's got to be higher. Okay, and for the continuation values, you got those optimal profits forever. Okay, and never had to pay maintenance fees. Okay, so we know they're going to be higher. Okay. Okay, so this convergence. The run that you're going to see is a 500 million run. It was the first one we did. Okay, and that was the R squared. This L squared P norm was that's essentially machine precision for this problem. Okay, but the truth is, it's sort of flattened out between 250 and 350 million iterations, and I'll give you times on that in a second. I'll quickly tell you about the approximations. It did well if you did the equilibrium, with 4, 5, and 6. You needed 5, but you didn't need 6. 6 and 5 were essentially identical, but 4 and 5 were different. Okay. Similarly, if you kept a 5-period history, okay, you did about as well. But if you just kept the last time the guy went down, you didn't do good enough. You needed the whole history of so not only did when it last time, but who else was going down when I went down last time. So I think this is time, I'm not going to go over this in detail, but what it's saying is with a fine enough partition, you get it. And there's only a question of how fine, and that's going to be example specific. Go ahead.
Sorry, I think I missed the specification of what the guys observe about each other.
Just the bids?
Just the bids.
That's the bids, and that's it. I'm going to do a restricted experience-based equilibrium, so they know the primitives. To do the restricted one, I have to be able to calculate what would happen were I to do something different. Is that clear? So I have to be able to calculate. I have to know the primitives in order to do that. Okay. So I'm going to compute a restricted one here, which took more time. So this is that. Here's the kind of time it took. It's quite a bit, by the way, and the full information took 1 hour. Okay, and you can see the restricted experience-based equilibrium, which allows you to get all the W's for the recurrent class. Takes quite a bit of time. By the way, the non-restricted one looks just like the full information one. It's just down to 1 or 2 hours. It's the restricted one that costs time. Okay. Okay, so You can see also that the computer time of these things, it's essentially linear in the number of states for each guy. These are the number of states that you need in the recurrent class for each of the equilibria. I'm sorry, this is a big firm number of states, small firm number of states. Okay, and you can see in the full information, that's as many states as you need, 3,500 for a full information equilibria. But now you've got to carry information. You've got to carry information on what the guy did in the past, okay, to predict. Okay, so you're getting larger ones. And if you go to 6 periods, you can see it's growing quite a bit, and the time is almost linear in the number of states. Okay, so that's the problem, and the problem is going down in memory because the actual computation to bring something up is quick. Once you got it up, it's easy. Okay, it's just going back in memory, and as there's more, you've got to go back farther down. Okay, so that's what's causing the problem. Okay, I think, by the way, the thing I took away from this is this is a pretty simple problem. If we're actually going to do applied work, we'd want a more complicated problem than this. What I took away from this is that even for this simple problem, that's a lot of stuff to hold in memory. 181,000 states or 200,000 states. And for richer models, it's going to become problematic. So in 2 ways, it's hard for us to analyze and probably harder to believe that agents actually condition on that much information.
I think that if you had a different kind of algorithm, you might have to hold less in memory. If you had a more local, distributed, synchronous algorithm, it might allow you to,
synchronous, I don't know. Local, I think that's true.
Local,
if I could do averages in an area or something,
yes,
that would help. I think that's right. We haven't gone that route, but I think that's probably right.
Yeah, that's what I was talking about with like a belief propagation type algorithm where you're getting consistency over areas locally.
Right. From an empirical point of view, I think what you want to do is you want to look for what the agents are actually conditioning on. You should be able to see this in the data set, right? Because their policies are a function of what they condition on. So developing a set of tests for that would be a useful way of going about it. Okay, so now I'm going to show you some quick results. I'm almost over. So these are some results. So let me just show you what's going on. This is a social planner. This guy's the social planner results. Okay, this guy's the asymmetric information results. Then the full information results, and then I've changed the primitives in a way I'll tell you in a second. Okay, I'm going to highlight a few things that are sort of interesting. It's pretty clear what the social planner does. Okay? What the social planner does is he shuts down 15% of the time, and every time he shuts down, he does maintenance. Okay? He never shuts down just for no reason, because there's no reason to do that. Okay? And when he does maintenance, he does it almost all on Sunday. You'll see that these are the number of operating generators. Okay? So he's doing almost all his maintenance on Sunday, and during the weekday, some on Saturday, and during the weekday, almost the 2 machines are up almost always, unless something goes really wrong. Okay? And it's similar for the small guy. Remember, he has 3 generators, not 2. Okay. So now, what happens with asymmetric information? We actually go down more. Okay, but we do maintenance less, much less. Okay, and that's so. Some of the time we're going down and just doing nothing. Okay, we're just leaving it down because we think we can earn money on our other generators. Okay, and that's the same for the small guy and the big guy. Okay. And yeah, and they do more on Sundays and Saturdays, and everything that you would expect happens. Okay, so this is the Nash equilibrium. The interesting thing is down here. So 2 things. One, the planner's doing more maintenance than the asymmetric information guy. Okay, but as a result, he has lower variable costs, both of them, than the asymmetric information guy. And the average cost is much lower for the planner than the other guy. This despite the fact that the quantities of the planner are larger. So it's an increasing cost industry because each of these cost curves are going up. Is that clear? This guy's producing more at a lower cost. And the reason he's doing that is because he goes down for maintenance more, and he comes up at a lower cost all the time. Okay, and it's not in the incentive structure. Okay, so the other thing to notice from this, and I'm going to tell you one more thing, is no matter what you do in this game, even if you're the planner, there's a huge jump in prices between weekdays and weekends. Okay, this isn't as dramatic as when it gets to 105 degrees in California, but it's pretty dramatic. It's a 20% increase between Friday and Saturday. Okay, and then Sunday it's 20% down, Monday it's 20% up again. Okay, so it's pretty dramatic. And you can't, and that's in this, you can't fix that. That's the best you can possibly do. Okay, because that's the social planner solution. Okay? So just my last word. The other thing we did is we said, okay, exactly the same thing, but cut demand in half. So now there's more capacity per unit of demand. Is that clear? Okay. So this was a surprise to us. Okay. Whoops, sorry.
Weekend and weekday prices now, kind of.
Yeah. So look what happens to the asymmetric information guy now. Okay. He doesn't change during Saturday or weekday.
Yeah.
Okay. Neither does the small guy. Okay. And the price split between the weekend and the weekday gets really small again. Is that clear?
Yeah.
I can show you what happens, but consumer surplus goes way up. Okay? And the reason is very clear. What's happening here is on Sunday, what happens on Sunday is everybody wants to go down on Sunday when there's asymmetric information. Why do you want to go down on Sunday? Because if you go down on Sunday, your competitor will think that your machines are up and ready to go on the high-priced weekday and you're going to bid in, so he might not bid in. Is that clear? When there's lots of generators per unit capacity, that's a very unlikely event. Okay? And that goes away. There's no more of that. And that's what's causing the difference in price between the weekend and the weekday. It's just sort of interesting, okay? I don't know, so there's a question of what's the cost of having more generators and things like that. Okay, but it's never been asked in this way before, I think, in the literature. So this was the closest thing to empirical that came out of this, and I finished. Okay, I'm happy to take questions. Yeah, go ahead.
So once you cut the demand in half, if there was a social planner, would he still go down only for maintenance, or is that no longer true?
We didn't do the social planner. My guess is he would only go down for maintenance.
I would guess the opposite.
I don't, so...
Because there is the cost of just being on in the first place, right? I don't know if it's in the model, but...
Yeah, you're right. I think what would happen, I don't know what would happen. I didn't calculate it. But he might have stayed off for long periods. He might have just shut down one generator forever. Because there's no sense in bringing it up, because there's a cost of going up. Remember, by the way, in the real market, not in this market, but in the real market, the part of the when you go up and down, this is when the cost can really go up. This is when you can hurt your generator. Okay, so if we were doing this in reality, you'd want also a stochastic thing that's a function of the amount of time you got up and down. Okay, that's what the guys in the industry say.
We asked most of our questions during the
Yeah.
we weren't shy.